Hi everyone, this is Siddharth and thank you so much for watching The Diligent Educator. If you like the video, do not forget to hit that like button and subscribe to my channel. In every video that I post, I always attach a link to an exercise document. Do check the description, click on the link and practice the exercise questions. If you have any doubt, post them in the comment section below and I'll get back to you. So having learned about the basics of electronics and some basics and symbols of circuit diagram, in today's lecture we'll be talking about series and parallel combination of resistors. Now these are the two very popular ways in which the resistors are connected. In case you are not understanding what I'm saying, go back to my previous videos, the basics of electronics, and do check it. Let's start with the series combination. So in series combination, as you can see, I have taken three resistors R1, R2 and R3. They are connected one after another. Now how to identify series combination and how to identify parallel combination we'll talk in detail in the later part of the video. For now, these are the three resistors connected in series, that is one after another. Okay, and let us assume that V1, V2 and V3 are the potential drop across the three resistors respectively. Also we know that since it is connected in the circuit and a battery or a cell is attached, some current will be flowing in the circuit, current I. So if I have to mathematically represent this, I can say the V, the total voltage V, is equal to summation of these three individual voltage, that is V1 plus V2 plus V3. Now we are going to apply Ohm's law over here. In case you don't know what is Ohm's law, please check my previous video which talks about Ohm's law. So here I can say V is equal to IR from Ohm's law. V1 will be IR1 plus V2 IR2 plus V3 IR3. Now you might be wondering why am I not using I1, I2, I3? Because as you can see over here, the same current I is going to flow through R1, then through R2 and then to R3. So the current flowing through each of the resistor is same. Now let's move ahead. We can take I common here and in the bracket I will be left with R1 plus R2 plus R3. I can see that I gets cancelled. R is equal to R1 plus R2 plus R3. This R is written as RS, that is equivalent series resistance. In other words, if I have three resistors of, say for example, this is of 5 ohms, this is of 10 ohms and this is of 15 ohms, and if I have to find the equivalent resistance of the complete circuit, it will be 5 plus 10 plus 15, which is equal to 30 ohms. So what do we observe? We observe that in series resistance, the equivalent resistance is always greater than the individual resistance. So whenever you want in the circuit that the resistance should increase, you will connect the resistors in series combination. Let's talk about parallel combination now. So this is a circuit diagram for parallel combination. As you can see, the three resistors, again R1, R2 and R3, are connected one below the other. Again, how to understand whether the resistors are connected in parallel or series we'll be seeing in some time. For now, these three are connected in parallel. We have a cell with potential difference V and a current I flows in the circuit. Now look what is happening over here. When the current I reaches over here at this point, it has three options to go, and that is where the current splits. From R1, let's say the current goes I1, from R2 the current goes I2, and from R3 the current is I3. Okay, so in individual resistors, different value of current is flowing. So I can say I, that is the total current, is summation of I1, I2 and I3. That is addition of the three individual currents. As per the Ohm's law, if you remember, Ohm's law says V is equal to IR. So I can say I is equal to V upon R. So therefore, I can say total current is total voltage upon total resistance. Over here I have written RP because that represents the equivalent resistance in parallel combination. P for parallel over here. So I1 similarly will be V upon R1 plus I2 will be V upon R2 plus I3 will be V upon R3. Now you might be wondering why haven't I written V1, V2 and V3? In parallel combination, the potential drop across the three resistors is always same. So from here I can say V upon Rp is equal to V, I can take common, 1 upon R1 plus 1 upon R2 plus 1 upon R3. Here V gets cancelled. Final equation we are getting as 1 upon Rp is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. So what do you understand over here? In parallel combination, the equivalent resistance is always less than the individual resistance. What I am trying to say is, suppose you have three resistors, 5 ohms, 10 ohms and 15 ohms, and if you solve this, the value of Rp which you will get will be less than the smallest of all, that is, it will be less than 5 ohms also. So try this out and let me know in the comments. We saw that in series resistance, the equivalent resistance is summation of the individual resistance, and in parallel resistance, the equivalent resistance is the reciprocal, addition of the reciprocal, and you'll have to take the reciprocal again of that. Now this is only for 3 resistance. You can definitely increase it. Suppose if you have 4 resistance, you can add plus R4 plus R5 up till Rn. So it can go for n number of resistors. And similarly over here, you can add 1 upon R4, 1 upon R5. It can again go till 1 upon Rn for n number of resistors. We'll see some numericals on the same, but before that, let's try to understand how will we understand whether that particular combination is a series combination or is it a parallel combination. Let's see some examples. Having understood the series and parallel combination, let's see some examples. Now what you see over here is a combination of 3 resistors, R1, R2 and R3, and you have to tell me whether they are in series combination or parallel combination. Now to identify that, always look at one resistor at a time. Look at R1. R1 has 2 terminals. This is first terminal of R1 and this is the second terminal of R1. Look at R2. R2 has 2 terminals. This is one terminal of R2 and this is another terminal of R2. Now if you look at R1 and R2, you can see that they share one and only one terminal with them. That is, they have only one common terminal. Remember, whenever 2 resistors have only one common terminal, it is series combination. So I can say R1 and R2 are connected in series combination. Similarly, R2 has these 2 terminals and R3 has these 2 terminals. You can say R2 and R3 are again having only one common terminal. So in other words, R1, R2 and R3, all 3 are connected in series combination. Let's make this example as a numerical and see how we are going to solve this. If it is given R1 is equal to 10 ohms, R2 is equal to 15 ohms and R3 is equal to 10 ohms. And they are asking you to calculate the equivalent resistance Rs. Why Rs? Because we have understood that this is in series combination. So the equivalent will be Rs. Nothing but R1 plus R2 plus R3, which equals 10 plus 15 plus 10, which is 35 ohms. So equivalent resistance over here is 35 ohms. Let's see another example. Look at this example. In this example, we can see R1 and R2 are similarly connected as we saw in the previous example. But when we closely observe, we will find something different. Let's see. R1 and R2. So this is these are the 2 terminals of R1 and these are the 2 terminals of R2. You'll say again only one terminal is common, but no. If you look over here, this terminal over here, there is no component in between these 2 terminals. So they are called as short circuited. In other words, they are at same potential. In other words, they are same terminals. So I can say that these 2 terminals, these 2 resistors have both their terminals common. Now if I would have drawn it this way, you would have easily told me that this was parallel combination. All I have done is I have squeezed this place and I have extended this one and you get this particular arrangement. So if this is parallel, obviously this has to be parallel as well. Let's try to solve a sum. If they have given R1 as 10 ohms and R2 as 10 ohms and they are asking you to find the equivalent resistance in this case. Again, since this is parallel this time, 1 upon Rp will be 1 upon R1 plus 1 upon R2, will not go ahead because we have only 2 resistors in this case. It will be 1 upon 10 plus 1 upon 10. When you solve this, you will get this as 1 upon 5. So 1 upon Rp is equal to 1 upon 5. But we are interested in the value of Rp. So I can say therefore Rp is equal to 5 ohms. From the theory we have understood that in parallel combination the equivalent resistance is smaller than the smallest value. Let's see if it is justified over here. Our values were of 10 ohms each, and what we have got over here is 5 ohms, which is smaller than the smallest. Let's see one more circuit. Now look at this circuit. They are asking us to find the equivalent resistance between the terminal A and B. Now this is a combination of series and parallel. Let's see if you can identify it. Let's see. R1 has 2 terminals, 1 and 2 over here. R2 has 2 terminals, 1 is over here and 2. So I can say R1 and R2 have only single common terminal. So R1 and R2 are in series. R1 series R2. Look at these two now. Look at R3 and R4. R4 has 2 terminals, these two, and R3 has 2 terminals, these two. And you can see that these 2 terminals are short circuited or connected. So I can say R3 is parallel to R4. Let's try to solve these two separately. R1 parallel, R1 series R2, if I have to get the equivalent resistance of these two, it would be simply 10 plus 12, which is equivalent to 22 ohms. Let me call that as Rs. And now let's look at R3 and R4. I can say it would be 1 upon Rp would be 1 upon 30 plus 1 upon 30, which will give me Rp as 15 ohms on solving. Now there is a small trick over here. Whenever you have equal value resistance in parallel, the equivalent resistance is always half of that. We saw this in the previous example itself, and here also it proves correct. Now these two, Rs and Rp, how can we represent that in this circuit? Let's try to simplify it. Instead of these 2 resistors, R1 and R2, I can put one resistor of 22 ohm and call it as Rs. So this is how my circuit will look. Here will be Rs of 22 ohms. And instead of these 2 parallel resistors, R3 and R4, I can simplify it by putting a single resistor Rp of value how much? 15 ohms, which we have got over here. Now if you look at this, this is similar to what we have solved earlier. You can say Rs and Rp, they are in series. So finally our equivalent resistance will be Rs plus Rp, which is 22 plus 15. That will come out to be 37 ohms. This will be your final equivalent resistance. What are we trying to do in all these examples which we have seen till now? We are trying to replace a complex circuitry with a single resistor. In other words, we are simplifying the circuit. So if there are say n resistors connected in series of different value, I can remove all of them and put a single resistor with a value which is equal to addition of all these. Similarly, we had a complex circuit involving 4 resistors over here, which we brought down to 2 and finally brought down to a value of 37 ohms. In other words, if I have to simplify this circuit, if you remember something like this was the circuit, if I have to simplify it, all I can do is between the point A and point B, I can put one single resistor of 37 ohms and it will function same as this complex circuit was doing. So do not forget to go back in the description and click on the document link and solve the exercise and come back to me with your doubts. If you have liked the video, do like, comment, share and subscribe. Thank you so much for watching the video.